5 sessions of the 6 days refresher program on contemporary AI applications in healthcare, sponsored by AICTE-ISTE, organized by Department of Computer Engineering of Dr. D.Y. Patil Pratishthan's D.Y. Patil College of Engineering, Pune, for faculty members. I welcome all the participants for post-lunch hands-on session. Today, I am extremely pleased to introduce Mr. Suraj Kumar and Mr. Aditya Modi. Mr. Suraj Kumar is a research scholar at IIT Bombay. He has been involved in various projects at IIT, such as algorithm identification in source code of programming assignments, machine translation evaluation using bidirectional entailment, algorithm identification and course comprehension. Prior to the joining in IIT, he has worked as a software developer at Triple Point Technology, Pune, and as a research assistant on the project Bodhi Tree, which is a learning management and coding platform, in which he has been involved in the development, deployment, and maintenance of Bodhi Tree project, which is used by more than 500 faculty inside and outside IIT Bombay. He has been awarded as Best Outgoing Student of the Year, D.Y. Patil College of Engineering, Akurdi, in the year 2017. On behalf of D.Y. Patil College of Engineering, I welcome Mr. Suraj Kumar to this session. Our second speaker this afternoon is Mr. Aditya Modi, who is also a research scholar at IIT Bombay. He is graduated from Institute of Technology, Nirma University in 2018. He has worked on various projects such as semi-supervised platform for grading robotic tasks, e-yantra, and automatic character completion on Devanagari script. During his PG at IIT Bombay and internship at ISI Kolkata, he has built a terminal interfaced menu-based YouTube video downloader which can merge audio and video. Once again, I welcome Mr. Suraj Kumar and Mr. Aditya Modi for hands-on session on machine learning for healthcare. Over to you, sir.
Yes, thank you, ma'am. I'll share the screen. Let me know if it's visible.
Sure.
Is it visible?
Yes, sir. Yes, it is perfectly visible.
Yes, so yesterday we have seen, like Aditya was talking about how the vision means image part, how we can use the image in case of healthcare. He has talked about a lot of models like convolutional network and then a unit and so on, mask RCNN. So that was about his part. He has explained about how the image and everything can be used and can be applied in the healthcare domain. Now for this part of the session, I would like to continue with the text part, meaning what are the possible, sorry, one second. So how exactly we can use text in the healthcare domain, and what are the models we can use, what are the state of the art thing existing in this particular domain. So yeah, without further delay, we'll start. So basically, first I'll talk about some models, because see, if we want to literally work in the domain of text, we should understand some models. And then once we have an idea of model, then we'll see how we can apply. Okay, so then we can see how exactly we can apply the models in, like, for example, in the COVID-19 situation, how exactly we can predict what can be the future graph for the rise of the cases or the fall of the cases. So these are the few scenarios which we will be considering. So yeah, so that's the overview of this particular session. Now, yesterday Aditya talked about the neural network. So yeah, so in today's world, neural network is one of the model which we used in each and every domain, because it's one of the accuracy, or the, you can say the it works very well. So first I'll like to summarize something, like, yeah, so here you can see, one second. So here you can see I am defining a neural network in a very abstract way where this is the input. So yeah, let me just relate to the what Aditya was exactly drawing. So yesterday he was drawing something like these are the x1 and x2 input. These are some hidden layer, let's say h1, h2, s3, and there are some output layers. So yeah, so these connections will exist, right? Now, I will just use a notation, and the notation is I'll try to just represent this particular input layer with this simple block. Then again, the hidden layer with a simple block, and then again, the output layer with a simple block. Why I am doing is that we will come to know because there are some models, if we just try to represent in this particular way, it's easier to understand, to visualize, because if I just try to show all the connections with this particular model, I mean to say this neurons here and there everywhere, so it causes some trouble in understanding. So the first thing is like this is the simplification of the neural network, just a representation, nothing else. So yeah, this is the first thing. Okay, let me. Okay, so once we are yes. So once we are clear with this, let's come to the we know that in the textual domain, when we talk about speech or any natural language text, we know the sentence can be of, let's say, 5 length, 7 length, or anything. The length is not fixed. But as you can see, the network which we have seen yesterday, the basic neural network, the size was fixed, means we have told that the input size is 2, 3. So in our scenario, which we have drawn, we have taken x1 and x2 as the two input. But if we are in the domain of natural language processing, so there the input size, let's say I'm saying one sentence I can write, I am good. Other sentences like I am good and I do work and all those things, any sentence we take, the size is not fixed. And the neural network which we defined yesterday, it requires fixed input size. That's one thing. Then the second thing is like there is no dependency among the words. So when I write I am good, so here when I feed it to the neural network, I'll require x1, x2, x3 as input. Let's say I'm feeding I am good. So here the neural network doesn't consider whether the M should be considered, whether I should care for I and all those things. So this particular are the two demerits, I would say, which lead us to some new models where we can apply the variable length input and also we look at the dependency. So these are the basic two motivation why we are trying to look for some new models. Okay, so once we are clear with this particular thing that we require something new. So what exactly new we require? The first thing is that we require a variable input sequence handling. That's the one thing. And then the second thing is that we require the context, which is very much important. Now, here you can see there are few examples in medical domain or any other domain, because even if we are applying the image or the text in the medical domain, the idea, the model is same. The main difference lies in the data set which we exactly use. So that's why when I say medical domain, it's like the data set I am talking about medical. The same model can be used in any other domain also. So that's the main point. Now, yeah. So one of the example is like medical image caption or the description. So in this scenario, we can consider we are given some medical image, let's say X-ray or CT scan or anything like that. We want some description. We want machine to generate some variable length description that there is some fault in this part of the bone or something like that. So yeah, so this is one scenario. Then the how we can exactly handle is that you can see on the input side will provide some image, and on the output side So it is just a representation purpose here I am showing. So on the input side, we have the image, and on the output side, we have something called sentence. So yeah, so this is one way. I'll talk about this particular model in detail in the coming slide, what exactly this is, but I just here I want to motivate what exactly, why the need for recurrent neural network and what are the use cases. Yeah. So the next thing is like the sentiment analysis. So you can see a very common scenario in the healthcare domain. We have a lot of hospital customer visit over there. So if the customer is visiting over there, they may be happy with the hospital service or they may not be happy with the hospital service. So overall, we want to improve the service. If the customer is not happy, why he or she is not happy? So in that particular scenario, this problem, you notice we have something called sequence or the sentence over here, and I want to predict something called whether it is a positive sentiment or the negative sentiment. So that's one use case. Now the next use case could be like, let's say right now I am in India, but I went to Japan. So there a language barrier is very much. Maybe the doctor over there, maybe let's say I'm not so much fluent with the English language. So also their doctors speak in Japanese language. So a barrier is existing between the language. So the NLP can help us in that domain also via the machine translation or the language translation system. So here you can see basically that we have some input sentence as input. Let's say it is in the Hindi. I know Hindi. And on the output side, we also have a sentence, and let's say it could be a Japanese. So that is one use case which we can use. So there are a lot of use cases we can think about. I'm just giving few examples to motivate the network. Okay. Now the other use case could be like a video classification on frame level. So let's say we have some video and we want to exactly see what is exactly happening in each and every frame. So it can be useful for medical domain also. If we are doing some imaging in form of video, there we exactly want to identify what is happening at each frame. So that is one of the use case in this particular scenario. So overall, in this particular slide, I have talked about what are the possible 4 use cases of the NLP in the healthcare domain, and I have talked about some very high level block diagram, how exactly we can use. Yeah, so that's one thing. Now, I have talked about that I will be using the RNN. Now let's look at what exactly the recurrent neural network is, so that if we understand this thing, all the further models which I'm trying to explain, even the state of the art model transformer, so it will be very useful for us to apply in this particular domain. Now, if you just exclude this particular loop, then this entire model looks similar to the neural network which Aditya talked yesterday. Now we just introduce a loop and then it becomes a recurrent neural network. So now what exactly this loop is, we'll try to see what exactly this loop is. So basically, first I'll go to the next slide and I'll come back here. Okay. So yeah. So X1, X2, X3 till X T is the input exactly which I will be feeding to the system. So this can be of any length, variable length. Now, at each timestamp, let's say I am at timestamp 1, I will be finding some output. Here I am not showing the output, but let's say here also I am getting some output. Then again, I'll go to the next timestamp T2. Then what will happen? I will take the whatever the output was from the previous timestamp, then apply here. So on, this process will keep on repeating. So this loop which you are seeing here, that signifies at each timestamp I'm providing some input, then there is some hidden state, then there is some output. And when I say any network, whether it is a recurrent neural network, whether it's a neural network, it's basically a function. It's nothing more than a function. So you can see on the top, I can define what exactly this is. So the input XT is the input to the model at time T, and HT-1 is the hidden state. When I say hidden state, that means when I feed at time one something, it will produce some intermediate state that is called hidden state. And yeah, we'll get some hidden state for the next timestamp and so on. So this is the main idea of this RNN. So this loop, so basically a neural network with some timestamp criteria is called a recurrent neural network in a very short way. So that's the main thing. Here, as you can see, we can handle the variable size input because there is a recurrence relation. There is a loop in this particular scenario. So I can handle 10 length input. I can handle the 20 length input. I can handle any length, 100 length or 1000 length. Now, the second thing is you can see when I am feeding at first timestamp. Okay, it will be better to go to next slide. When I am feeding at first timestamp something, I am getting something as a hidden state for the next timestamp. So see, in the next timestamp, this T2, there is some input and there is some hidden state. So you can see there, this function is taking two things as an input, the current input and the previous hidden state. So this is basically what the RNN is. It considers the context also. So overall, you can see this H1 is like behaving like a context because X1 we have given as input, it has given some intermediate output H1. So yes, so this is what the RNN is all about. So just to summarize, we use RNN for variable length data. We use RNN when we require to consider the context between the input words. So these are the two things. Now the next question comes is that at pen and paper, I am able to see what exactly the model is. But if I have to apply in healthcare domain or any other domain, how exactly can I do this? How exactly can I apply? So the first step is data collection part. So data collection part can be done. So there are a lot of websites, like one of them is Kaggle. You can find a lot of data over there. You can go from there. And also there are a lot of other papers which talk about the data, some other paper which they collect the data, they host on their personal college or university server. So if you look at some of the papers, so there also you'll find some of the source of data. So yeah, once the data collection part is done, now the next part will come, the modeling part, that how exactly we can model the problem at hand. So Aditya yesterday talked about like we can use convolutional neural network if we have image. In our case today, we are talking about the text. So we'll basically deal with the RNN, means recurrent neural network. So we'll perform the modeling based upon RNN. Now the next part is the loss function, because as we already seen in the previous slide, we have what is a recurrent neural network? It's a function, and where this W you can see it's a parameter. It's a parameter of the network which we exactly need to learn. So what exactly makes us possible to learn this? The loss function, which talks about at each iteration how much error we are trying to make. So that's what the loss function. So yesterday we have looked a lot of loss function, like some mean square error, then we have looked about absolute error. So these are some of the loss function which we have looked at. Now for our purpose, basically sequence to sequence modeling, in most of the scenarios we model it as a classification problem. So the cross entropy is one of the loss function which we should actually care about. Now the fourth part is about the training algorithm. This fourth part is all about the training or the optimization algorithm. How exactly I can optimize the parameter. As I told, model has some parameter W, and this how well this parameter is defined by the loss function using some mean squared error or something cross entropy which I talked. Now how exactly we can get the best value of W? So that is done by the training algorithm. So training algorithm, there are a lot of training algorithm. One of them is back propagation, which we basically use for the neural network. So if you ask me in a go, what exactly the back propagation is? It's nothing but a calculus, means you just take the derivative and just try to optimize the parameter, because we know if we take the derivative equate to 0, we find something minima or maxima. So it's an intuition like that we can compare. But there we use some algorithms like gradient descent and all those things to actually use those derivatives. Okay. So this, so it's not about the healthcare domain also. If you want to apply the recurrent neural network in any textual data, the same pipeline will follow, because the only difference which comes is like data. In healthcare domain, the data is related to healthcare. Maybe let's say I want to do machine translation, something machine translation. So there I can take some data in Hindi or English and so on. So it's all about the data which makes it feasible to apply in domains. If we have data, we can apply in the domain which we want. Okay. Yeah. So now, till now, if you see, I have shown that there is only one layer I was using, but we can also use any number of layers. But the question is, why exactly we want to use more number of layers? The reason is that we know RNN, what exactly it does, it approximates a function. Sorry. It approximates a function from data, right? And if we want more complicated function, we can use more layers in between. So there are a lot of architecture variations which we can do, but here I'm just saying we can add more layer, we can get more complicated function. But a lot of variation is possible here also. Okay, so till here, if any question you guys have, so that because right now I have only talked about the RNN, it's better to clear if any questions we have, so that now we'll move on to some other models. We'll see what are the disadvantages of this model, and then. So do we have any question, or we can proceed?
Participants, do we have any questions?
Okay, I think in the last we can take if we have. So I'll just.
Yes, sir. Sure, sir. Yes. Okay. Please continue.
Yes. So there are few problems with the RNN network. Like if you see, I told how we train the RNN, we use the back propagation. So there we find out the derivative. And the derivative can be small enough or derivative can be large enough. So if you see, let's say we have a sentence of 100 length. So there you can see, you can imagine. So here you can imagine we have a input of length 100. Now if we try to find the derivative at this point of time at 100 input and try to propagate till the starting point, the first input. So at each step, the gradient will become lower and lower and lower. As a result, we will not be able to impact this weight corresponding to X1 input so much. So as a result, we are not updating the W1 weight as required. So this particular problem is called vanishing gradient problem, meaning if the network is too long, like here I have taken a 100 length example, in that scenario, the W1 or W2 or W3 is not getting so much impacted by the gradient because the network is so long. Once the gradient try to reach here, it vanishes, it get a very slower. So there is a reason related to this in the activation function also, but that part I think I can skip here right now. But one of the reason is as the network length is more and more, the vanishing gradient problem is more and more. So this is the problem with the normal RNN network. So the next question is what exactly we can do, because in the real world scenario, you'll see a lot of sentences are very long. So we have to solve this problem somehow. So how exactly we can solve this problem? So we can do something, and the things are like, see, I told there is a X1, then there is some H1, X2 input, there is some hidden state H2. Let's say right now I am at X50 and H50. Now, when I am at X50 input and I am trying to do some maths over here with the function I already defined. So here one of the question is, should we remember the entire history? That's one of the question we should ask. Or should we try to forget something? So that's one of the way via which we can avoid the problem of the vanishing gradient. Then also whatever input we are providing, how much significant that input is, that's the another thing. And the combination of these two, how much exactly we can pass it to the X51. So there some input X51 will be there and hidden state H51 will be there. So these are the three techniques which exactly we can use to avoid the problem of the vanishing gradient. So yes. Now, so with this particular three techniques, there are some models which people have developed, and these models are not nothing new. These are some came in around 1999. So there is some model called LSTM, long short-term memory is the full form, and there are some network called GRU. There are a lot more network, but these are the two commonly used network. And even I have worked with LSTM for music generation and all those things, and it works pretty well there also. So yes, so these are some models. So I'll just try to motivate these models in a sense that what exactly we do in this models. So here you can imagine this is like a RNN shell which I was talking about. What LSTM exactly does is like that. It does some operation, some maths in between this particular RNN so that the vanishing gradient problem goes away. So when I say vanishing gradient goes away, you can see here, you can see over here, there is some activation function. This is one activation function. This is another activation function. Here is also some activation function. So it is one of the way to do this. There are a lot of other ways we can do this. So there is a mass behind this, how exactly it works and all those things. But there are three components overall. This is one component. This is another component. And this is another component. So one of the component is about forget. This is about forget. This is about selective read. And this is about selective update. So these are the three mathematical unit you can say inside the RNN, which try to avoid the vanishing gradient problem. And yeah, when I was reading this model for the first time, even I was confused what is happening in this model, what maths and all those things, how these things are happening. So if we go into the details, we find out. But for time being, I think we can assume that we have three units overall. Those three units are like something forget, store, and update. And it's nothing but a mathematical combination something. And if we use this, just think the vanishing gradient problem will go away. So that's the overall idea of this particular LSTM, long short-term memory model. Okay. Now, so I have talked about RNN. Then there is a problem in RNN called vanishing gradient, and the problem can be solved using the LSTM models. And it's before 2017, this model was predominantly used because it is one of the best model. But 2017, we'll talk about what exactly happened and what led to there was a model by Google which totally revolutionized the world of the NLP. So yeah, we'll talk about that also. Even few people use the LSTM nowadays also, but transformer is the model which we'll be talking soon, and that's the model which we should use if we want to get the better results. Okay. Yeah. So in the beginning, I have talked about that there can be a barrier in communication between a patient and a doctor. Or let's say, even if I'm going to a hospital, there can be a barrier in communication because of the language, different languages we work on. So how exactly we can solve that problem? So yeah. So yesterday also Aditya was talking something about encoder and decoder in some sense. So here also you can see we are providing some input sentence in some language. Let's say it's a language XYZ, and we are getting some output in a language called English. Now this particular thing is like a RNN. This entire thing is a RNN. And this entire thing is also a RNN. So here you can see using RNN, I can solve the problem of machine translation. I'll provide some input in some language. Let's say here I can take Hindi also, and here I can find out the translation in the English language. Now, so this is one of the architecture which we can use. So obviously we can code this using the libraries like PyTorch, TensorFlow, which Aditya talked about. But instead of talking about the coding of this part, I'll talk about the coding of the transformer soon. So yeah, now here you can see, first we are reading the sentence in the input language. Then here, whatever output I'll get, I'll feed to the decoder, and then it will try to convert into English language. So let's say in this scenario, our sentence length is 3, but there can be a situation like I can go on speaking and I could talk, let's say 200 word sentence. So in that particular scenario, we are using the output is actually here. If you see, we are getting a vector. So this entire model is maths, and the input we are giving vector, output we are getting vector. Whether it's a 3 length input or whether it's a 200 length input, we are getting a vector of some dimension that is a fixed dimension. Let's say 700 dimensional vector is there, or let's say 500 dimensional. These are the hyperparameter which we can try to select. But yeah, so here we'll get some vector maybe for 3 word also, maybe for 200 word also. But a problem will arise if we have a sequence length of larger and larger, 200, 300, 400. So there is a bottleneck problem, because in this 200 dimension, or let's say 500 or 700 dimension, I am not able to accommodate all the information because the sequence length is very long. So this is the problem in this particular model. And even let's consider a scenario. If someone has given a paragraph in Hindi and they ask us to translate into the English language, so is it the case that we'll read the entire paragraph and then try to convert into English language or translate into English language? I think we'll do sentence by sentence, because we can't remember the entire context at once. We may forget the things once we have read the paragraph. So we'll take one sentence, we'll translate into English, take next, translate into English. But you can see whatever model I have explained for machine translation, here I am consuming the entire input, the paragraph at once, try to remember it in form of some vector, and then try to translate into some other language. So this is something here, something fishy is looking, that this is not something how we work, because the neural network is inspired from the humans and human brain. So yeah, so there was a need for something like some incorporation in this model, so that the model should behave as we humans could have solved this problem. Yes. So the problem, as I discussed, was like whole sentence we are trying to represent into a fixed vector. Yeah. So one point I want to emphasize over here is that I'm always talking about vector, but before that, I was not talking much about the mathematical formulation, because it's better to abstract those things. But the vector, as I explained, is the vector. When I say vector, I'm getting some output of the encoder. That is what the vector I'm talking about. Okay. Now I have already talked about the solution. The solution is focus. Focus on first line. Focus on second line. Focus on third line. Do one thing at a time. So that's what the solution is. So the model name which machine learning literature usually uses like attention. So they are saying in RNN, the model is same. They are trying to add some attention, just like we humans do. So that's what the entire model is all about. So you can see here in the diagrammatic form, the encoder part is same. There is no difference. The decoder part is also same. There is no difference. But there is something which we got over here that is called attention. So this is basically, if I have to talk in terms of math at a very high level, so this is a neural network, feed forward neural network, which was the first topic of Aditya he talked yesterday, like neural network, a multi-layer perceptron. So this is like that. So how it works internally and all those things we'll try to skip in this particular presentation, but you can think there are some weights here also and all those things, and somehow some maths is happening here and it is trying to focus on some specific part. So that's how it works. So yeah, while looking at diagram, we'll get a very basic idea of this particular thing, but there is an entire math behind this, how it works. Okay, so if this idea is clear, we can proceed, or if any question is there for this particular part, we can take here that what exactly attention is, or if you want to explain in detail attention, like maths, some maths, I can also go into that. So should I, if anyone has any doubt for this, you can ask. Attention, why we came with this attention, or
Yeah, so I don't have a doubt, but so that I would just like to clarify it with an example that we generally have this ambiguous words like the bank. So bank would mean a money bank, and then bank would mean river bank, and so on. So many words change their meaning, change their roles per se based on the context. So what attention tries to do is, for instance, if we are trying to decide whether bank means a money bank or bank means a river bank, then attention just tries to focus on the sentence. So if we have talked about fishes, water, river, then all those contexts aggregate together and makes us want to conclude that, okay, we are talking about a river bank. But if we are talking about finance, money, cash, something of this, if these words are present, then that bank would mean a bank, like a money bank. So attention is just focusing on the sentences, focusing on the hidden encoded vectors, and then trying to make a decision by carefully choosing which components are going to play an important role in deciding the current word, the current context of the current word. I hope that goes well, Suraj.
yes, I think that was explained well. Yes, so I'll just move on. Okay. So just to summarize what I have talked about RNN, then it has some problem of vanishing gradient. I talked about LSTM. Now LSTM was having some problem in focusing the longer sentences. So there we talked about attention. Now these three models, whatever we have talked about, it has one major problem, and that problem is the sequential computation. So what exactly is this problem? You can see when I talked about RNN, there was a recurrence, there was a loop. That means at each timestamp, let's say I'm at timestamp 20. It can't be calculated until I have completed 19 timestamp. So there is a sequential computation going on with RNN, LSTM, or even with attention plus RNN. So this is a very major problem, because before 2017, people used to train the RNN or LSTM for almost a week or 2 weeks or even a month, depending upon the data we have or how deep the network is. So it was a very problematic task because we can't parallelize this. The reason this recurrence, it was a very major problem, and the NLP natural language field was just trying to digest this thing that can be parallelized. So this question that how can we exactly parallelize this particular model? So that was the question. So the solution was given by Google in 2017, and it totally changed how the NLP scenario will look. So in the 2017, Google published a paper called Attention is All You Need. And it's a major breakthrough in the natural language processing. Why major breakthrough? Because it removes the recurrence part. This recurrence part, which I was trying to talk about, it was totally eliminated by this paper. And currently every state of the art model uses this particular transformer model. So the model is called transformer, and even there is a story why they named it transformer, because it transformed the NLP domain. That's why transformer. And yeah, and Google is working great in this particular domain. In 2020, I think 2 months ago, they further improved the model, but I am not going to talk about that model. I'll just name that model. There's a model called reformer. They further modified transformer in some way, lightweight, because transformer is somewhat heavy in terms of uh, how exactly the parameter, heavy in terms of number of parameters. So reformer model they introduced in, I think, 2 or 3 months back they have introduced. So yeah, I haven't worked practically on that model, but I follow the literature, so that's why I know this name. So Google is one of the big player in this domain, because these two major breakthrough was by Google. So yeah, as I told, there was a revolution in NLP domain because of this particular transformer model by Google in 2017. Yeah, so I have just taken this picture from the paper, Attention is All You Need. Right now, if we see at the model, it looks very complicated. At least when I looked at this model for the first time, it felt like, what is this? I can't understand. There is some into and that side and all those things, some connection going from here to here, some positional encoding is happening. So there is a lot of complications here. So instead of, I just showed you this diagram, it looks very complicated. But when we read about this particular model, I'll just simplify the model and try to explain. You'll find out it's a very intuitive model and it's a very simple model. There is nothing great about this model. It was just an idea of striking with the people. Yeah. So at a very high level, you can consider transformer as a black box, which takes some sequence. In this case, let's say a sentence in some XYZ language, and it produces some sequence in some English language. So transformer in a nutshell, we can say it's a sequence to sequence model like RNN or LSTM. So at a high level, it is like RNN. Now, let's try to see exactly what is there inside this particular black box. If you see, there is encoders layer and there is decoders layer. Just like in RNN machine translation, I talked, there is some encoder this side, then some vector comes, then some decoder is happening. Here also the same thing is there. Nice, it is matching with whatever RNN was. Now, this entire encoders layer consists of a set of encoder. So in the original paper, I think they have put 7 or 8, exact number I don't recall. Yeah, so there is a set of encoder layer and all the layers are similar. There is nothing different. It's just about stacking one layer on top of that. Same thing for decoder. They have stacked a lot of decoder layer. Yeah, so this is done. Now let's try to look at what is exactly inside each encoder and what is exactly inside each decoder, so that we'll get a feel of how the recurrence was eliminated. So inside each encoder, we have a feed-forward neural network, or the other name is multi-layer perceptron as used by AICTE yesterday. And there is something called self-attention. So this is the very important part which led to the removal of the recurrence, which was causing the sequential problem. So we'll look at this self-attention, what exactly. So you can imagine the similarity between the name self-attention and the attention which we have studied earlier, Like we have talked now, if we want to do machine translation, we need some attention to focus on what input exactly. So yeah, so this is related to that part only, but somehow in some other sense, I'll talk how. And in the decoder, same feed forward is there, same self-attention is there. And there is one more thing called encoder-decoder attention. This is exactly same as what I have. This attention over here. This is also known as encoder-decoder attention, because it consider encoder also, it consider decoder also. That's why the name. So in the decoder side, everything is same like encoder, except the encoder decoder attention, which we have already seen. So now, once we are ready with the architecture, like as I told, I'll just recall again, transformer is a black box. In this black box, we have encoders and decoders, and the encoders consist of a stack of encoder, and decoder consists of a stack of decoder. And in each encoder, we have a feed forward neural network and self-attention. And in each decoder, we have something called feed forward neural network, self-attention, and one thing extra from encoder, that is called encoder decoder attention. And this is same as what I looked at RNN with attention. So this is the exactly same thing. So we are getting the architecture is almost similar what we have studied, but this self-attention is what removing that recurrence part. So this is something very much important. So now let's understand what exactly this self-attention is, which led us to the remover of that recurrence part of RNN. So let's take an example. The animal didn't cross the street because it was too tired. Here it can be referred as a human. We know it refers to what we know the language very well, but computer doesn't know. Computer, maybe it can say it referred to animal, it can refer to street or any other thing. Computer can be dumb enough also, it can refer if not properly trained to cross also, because it doesn't understand the language, it just understands the 0 and 1s. So yeah, so the main question is which self-attention addresses is each word in the sentence refers to what exactly other word, or maybe context you can say. Indirectly, for each word, we are trying to see what word which is trying to influence this word. So here you can see this diagram. On left hand side, the same set of words are there, and on right hand side, the same set of words are there. Here you can see it. Here you can see there are a lot of connections to all the word. It's a probability. Here you can see darker the color, more probability is there. So you can see it can refer to animal, the, or anything like that. So this is what exactly self-attention is trying to learn. So in short, if I have to say what exactly self-attention is doing, it is trying to consider the context, and at each word this operation is happening. And you can see if we have the entire sentence available to us, we can process each word parallelly because there is no dependence. When I'm processing didn't word, I can see the left, right completely. When I'm at it, I can see the entire left and entire right completely. So this is the main idea. That is, I'll consider the context being at each word, looking at left and right. So that's what the context is all about. And that's how self-attention is trying to remove the recurrence part. So this is very important, this self-attention. So self-attention we have covered. So for sake of simplicity, I have just talked self-attention, but in reality, model uses 8 sets of, they find out 8 set of self-attention. So what I mean by that is that they find self-attention for the same word 8 times, first time, second time, third, fourth, fifth, so that they try to see the all possible cases. We can try with 9 also, 10 also. So these are the hyperparameters which they have experimented with, and 8 works very well. So that's what this is all about. So they also call this multi-head multi-head self-attention because they are calculating it multiple times. That's why it's called multi-head, and they try to look at different context. Yeah, so that's what it is all about. Okay, now let's go back to the transformer which I have discussed, which I have taken from the paper. Here you can see multi-head attention is there, which I have talked about. Feed forward is there, I have talked about. This entire thing is called encoder, and then there is something, it is repeated n times. Here also feed forward is there, multi-head is there, mask, multi-head. So let's just forget about mask right now. To simplify, here is also multi-head attention. So these three things are there. Also apart from that, you see addition and normalization. So these are just operations which we perform so that the data, whatever data we have, we try to normalize in some range. Because see, if we feed the data directly after operation, some data could be in range, let's say 0 to 10. Some data could also be in the range 100 to 200. So data, we want data in the similar range so that the training can become faster. So that's why you can see there is some normalization and all those things done. And also there are some residual connections from here. Why we try to do that? Because we don't want to lose the initial words, vector, whatever we have. So overall, this is the thing. Also, I'll just take 2 minutes to talk about embeddings. As I already told that whatever model we are talking about, whenever we talk about machine learning or deep learning, it's nothing more than a maths. Everything is maths, statistics, everything like that. Now, we are in the natural language domain we are talking right now. We can't feed the natural language directly. For that, we have to convert the natural language into some vector representation, right? So that's what, so converting the text into vector, that process is called embedding. So that's why first we have input, let's say I study in IIT Bombay. So first this particular sentence will be converted into vector using this layer. So it is also it also has parameters like weight and all, just like we have feed forward network. Yes, and also apart from that, we have something called positional encoding. So why that is important? Because let's say I feed another sentence, IITB in study. So for each word, we can convert into vector, but order is also important here. Otherwise, it doesn't make sense. So there is something called positional encoding, which talks about the position, relative position of each and every word. So these two things are covered. Now, one thing is that how exactly we can convert into a text into a vector. So that's a question we should care about. So there are a lot of things. Let's say I talk about, let's say we have a very small vocabulary, like I love Python, let's say. Now, let's say I have only 3 words right now in the vocabulary. Now I can use a 3-dimensional vector to represent each word. Let's say I can be represented like 100, love can be represented by 010, and Python can be represented by 001. So this is the very basic level of embedding which we can do. When I say embedding, text to vector. So this is a very basic. There are some other embeddings which exist in literature and which were used and currently also used, but after transformer, the things have totally changed. So just to name a few, like we have something called word to vector. So as the name suggests, we have some word, it will convert into vector. So yeah, so there are some algorithms for this also, how we do the entire process, the paper. And luckily, as I recall it correctly, this was also given by Google. So Google is very actively doing a research in the NLP domain. Yeah, it works in image also. It's not like that, but NLP, a lot of contribution I can see. Okay, so also on that, yeah, so I have talked about this particular part, encoder, decoder is done. This embedding is done. Now, this part is remaining. So basically you can consider I have to produce some output. I have to produce some word in case of machine translation. So there I'll use some some linear layer and some softmax. Why exactly? We exactly want to try to convert whatever output we are getting out of decoder, so into some probability distribution. Like say we have a 3-word thing, and this softmax, if we apply, it can say like probability of I is 0.9, probability of some love is 0.05, and probability of this is 0.5. So exactly, let's forget about this layer in so much detail right now, because that will vary upon what exactly purpose we are using this transformer for. We can use transformer for a lot of purpose, like classification, sequence to sequence modeling, or anything, any textual task you can use this particular model for. So it's just for machine translation I've used the softmax. So yeah, so just forget about this part right now. Depending upon the task, we'll define loss function, we'll define the output layer, what exactly we want at this point of time, and try to optimize using the backpropagation algorithm. So that's how this architecture was introduced, and that's how this works. And I'll show you the code for this also. Maybe that will clarify better, but towards the end of the session. Now let's try to. Yeah, so now I think we are done with the transformer. If anyone wants to clarify anything for this, we can take the question. Because this is very important architecture if you want to work in the field of NLP in any domain, healthcare or any XYZ domain, any domain, you'll use transformer a lot in today's world.
Participants, do we have any questions for this section?
Okay, I think.
Okay, right. Yes, you can continue, sir.
Okay. So the next part, so right now I have talked about some models like RNN, LSTM, attention with RNN, and transformer. I have talked about 4 models. Depending upon data, I can use it for any other purpose. Now there are 2 ways in which exactly we can use these models. One way is that we can train from the scratch, means we have collected some data set, we have some model. Using this data set, we'll try to get the model parameters, weight, whatever you can say. That's one thing. And that's a very good way to proceed if we have a large amount of data. Why? Because if we are right now, we are in the domain of neural network or the deep neural network. So it's a data hungry network. So if we have large amount of data, we can train the entire system from scratch. But suppose we don't have large amount of data, what can exactly do? Like in case of Indian languages, in speech at least, we have even speech and text also, we don't have so much large amount of data to work with as required by the deep learning, because deep learning require a lot of data. So there, what exactly can we do? We can use the transfer learning concept. So this is a very beautiful thing, I think, and used a lot for low resource language. So how exactly this work is that we train the model on huge data dump. Whatever the huge data dump we have, we can train the model. And then depending upon the task we have, let's say we want to classify the diabetes, that there are 2 types of type 1, type 2 diabetes, the data could be less. So we first train the model on some previous data, whatever we have, and then we trying to fine tune. I think instead of diabetes, let's look at the sentiment analysis that will motivate it in a better way. Like we know, English language is a fixed thing. We have the entire Wikipedia. We can crawl the data, the grammar, everything we can learn beforehand. And then for sentiment analysis or any other task, spam classification, if we have the less amount of data, we can just try to train our model. Once it has learned the grammar, we'll try to train our model on the particular task. So that's what the transfer learning is all about. And one thing is very important you can note here is that we can't apply transfer learning always, because see, For sentiment analysis also, we have something called, we look at the language, right? So if we have some overlapping between the tasks, then only we can apply the transfer learning. So what exactly I mean by that is, I'll go to the next slide. So in the transfer learning, we have two steps: pre-training and fine-tuning. So pre-training basically means I'll try to learn something, let's say language representation of English. And in fine tuning, I'll try to, let's say, spam classification is what I'm more worried about right now, email spam classification. So in spam also, you can see the English language, the text is what exactly matters, right? So if we learn that English language beforehand and then try to retrain our model. When I say retrain, I'll start with this model and try to retrain on this particular spam classification task. So it's a very good way to achieve this particular thing, and the accuracy and whatever is there, it's a very good score you'll get. Okay. Yeah, so there are a lot of pre-trained model. If I just go on counting, it will be more than 100, but there are few important pre-trained models or transfer learning models, you can say, which I have listed down. GPT is there. This is by OpenAI. They are also working very great in this field. Then we have something called BERT model. So this BERT model is exactly based upon, so whatever model here I am mentioning, these are the model after transformer was invented. Transformer model was invented. And these models use the transformer as the base unit to define the model, to pre-train the model. Okay, so we'll look at the BERT in detail, exactly what and how exactly. But in a nutshell, these are the models. Okay. Now, as already talked, in the transfer learning, we have two phases. One is the pre-training and one is fine-tuning. So let's come to the pre-training and understand in a short what exactly this is. Pre-training is usually done on the unlabeled data. Like we can crawl the Wikipedia data and try to do something so that we learn the language. What exactly we'll do, we'll talk about that. Also, if you remember yesterday, we talked about supervised learning and unsupervised learning. Here we have data plus label. Here only we have data. Now, there is a third type, which I think I just talked about at a very high level, semi-supervised. So here we have only data, but somehow during training, we try to generate label. So that's why it's called semi-supervised. It's a supervised, but we are trying to find what label exactly is there. So this is the pre-training stage, unlabeled data and semi-supervised. Okay, so for example, unlabeled data, you can take Wikipedia, dump Wikipedia. Okay. So there are a lot of semi-supervised techniques which we can use to learn the English language representation. I have mentioned two of them, which are very easy over here. So let me just delete this because I need some space to explain what exactly these are. Okay. So let's say I'll talk about mask language modeling, which is a semi-supervised technique, and what exactly it does so that we are able to learn the English language representation, whether it's the grammar, whether it's a noun, pronoun, whatever it is. Let's say there is a sentence called, I love to code in Python. Let's say this is the sentence. So we try to mask the word. Let's say I have masked the word love. So there is a mask spatial token. So now I have modified the sentence to this. Now, since I have modified the sentence to I love to code in Python to I mask to code in Python. Now, a very common intuition which comes to mind is, what if we ask the model to try to predict this word? So if transformer model is trying to predict this word, it will look at left and right, right? So ultimately it will understand the things. And also we know the exact level of mask love. So you are seeing the relation that we are trying to generate some data which is labeled. So you can consider this as a data where this is the unknown part and this is the label. So somehow we have done this process, and this is done on the entire Wikipedia data. And also there are some book corpuses also, which is available, almost 150 GB or something. I don't remember the exact amount, but the entire data on which these models are trained. And these are very used models, we can't train on it on our laptop, but there is a plus side of it, which I'll talk about. Okay, so this is what this task is all about: mask language modeling. As the name suggests, I'm masking something, and there is a language modeling. Language modeling meaning I'm trying to predict the mask word. So that's the first task. Then the second task is next sentence prediction. This is a very simple task, very mundane, very trivial task. The task is Wikipedia data is given to it. Let's say some sentence 1, sentence 2, sentence 3, sentence 4, sentence so on, still sentence n is given. I'll take these two sentences together. The label is that, yeah, these two are the sentence together. So we'll say it 1. If I take S2 and S4, these are not together, means not one after the other. I'll say it as a label 0. So somehow you're seeing I have the unlabeled data. I have converted into some labeled data. So that's what these semi-supervised methods are. So these are the two basic semi-supervised technique in natural language domain. So these are two basic things which was in, and after this, I think there are a lot of models there, like translation language. So let's forget about all those things, but there are a lot of semi-supervised method. Okay. Now, if we are clear with the pre-training part, then we know we have learned the language. We know what the language is. Now we'll try to apply to some domain. Let's say spam classification, let's say some other task, machine translation for patient-doctor communication, all those things. So here comes the fine-tuning part. Fine-tuning is done on the label data. We have the label data, like in case of sentiment analysis, I have some sentence given. I know it is a plus, means positive sentiment, or the negative sentiment. In question answering, we have the question given, we have the paragraph given. So all those things are there. Classification, tumor classification, diabetes classification. So all those things are, so these are the label data given to us. Sorry. And as told, since we have the label data, it's a supervised technique we'll use. So what exactly we'll do? First, we'll take the pre-trained model. Then we'll apply on anything, let's say tumor classification. So that's how we can go about this. Okay. So till now, I was talking about transfer learning as a very general term. I haven't talked about any architecture. Now I'll talk about an architecture which was also given by Google in the year 2018. And Google search engine also uses a variation of this model. This is one of the model. There are a lot of variations which of this model also exist, but yeah, we'll talk about, but we'll stick with what very basic model. So there are two variant of BERT which they give. We can define our own variant also, but I'm talking about what exactly they did. So there is a BERT base and BERT large. There are two models. They just did one thing. We already seen the transformer model. There is an encoder there. There is a decoder there. They took the encoder from transformer, stacked one on top of other, 12 times, that's called BERT base. 24 times, that's called BERT large. So these are the two models which they have publicly open sourced. But there are some other variant we can try. You'll ask why 12, why 24, right? These are the hyperparameter. So these are they have experimented with, and some other parameters are there, how many spaces required and all those things. So let's not go into the detail of hyperparameter. But here my intention was like, transformer model is there. Take the encoder, stack on top of one another, you will get something called BERT, and use whatever the objective I have defined, like mass language modeling, next sentence prediction. So if we use all those things, we can say this model knows the English language, just like we humans do. Okay, now we are clear with this part. Now let's see this diagram which talks that in a nutshell. So we have an objective I have already talked about, language modeling. We have some book dump data, Wikipedia data. There is a BERT model. We do semi-supervised step to learn the language. So here the language is learned. Now there is something called email message is given, some class is given, spam or not spam. I'll try to take the existing model. I'll take this model, put it over here, put a linear layer as talked by AICTE yesterday, and then just do a supervised training, just like we do it for a simple perceptron or any other thing. So this is how transfer learning can help us. Now, one question you may ask is that, as I told, we can't, it's a very huge, this BERT is trained on a very large amount of data. We can train on our system also, but it takes a lot amount of time. So what exactly people did, they pre-trained the model, they got some weight, because I told there are some weight and the parameter. They published pre-trained model. So right now, if you want to do the email classification, you just have to load the pre-trained model. When I say load the pre-trained model, load the weight, and just try to classify. It's a very simple, the code is not so much difficult. It's a very straightforward way to apply to even a simple or the complex example. So this is how exactly BERT work. Okay, so I'll give a demo of this BERT model very briefly, and then we'll move on to the other things. So exactly, I am using the Google Colab. So I'm using the Google Colab. Okay, I don't remember the password. Let me open from here. I have already. Yeah. So Google Colab, if anyone of you want to try these things, you can go to Google Colab. You don't need to set up anything on the local system. So Google provide GPUs, TPU free of cost. Obviously, there are limitations you can't use for a long time. You can use for an hour or two with some limitations, but it's a very good resource to have. So I'll just walk you through the steps, and it's a very straightforward steps. So right now, I will be working with the computer of Google, the cloud of Google. So I'll install a library called Transformer. You can see here, we have a library called Transformer, which contain a lot of pre-trained model like BERT and so on. There are a lot of pre-trained model. I'll also go into what are the models, how you can find out. So just a simple line, environment is set up. No need to set up anything on the local system, done. So this is the output which we get when we run this. I'm not running it correctly, but yeah, this is the output which we get. Logs exactly, not output. Okay. Now the next step is like, if we code anything, we have to import libraries. So this torch library is already talked by Aditya. This is a PyTorch library, which is a very useful library if you want to work in the domain of natural language processing. Now, in the transformer library, this second import I'm talking about, in the transformer library, we have something called BERT for question answering. So this is a pre-trained model, meaning someone has already trained this language on Wikipedia data, And also we have some question answering. So this demo, what I am giving here is a question answering system using the BERT. Okay, so yeah. So BERT for question answering is something already pre-trained. So the demo which I am giving here right now, I am not doing pre-training. I am not doing fine tuning. All those things are already done by some person. So there is a Hugging Face library. So this transformer is provided by Hugging. I'll come to that also. I'll just walk you through the website of Hugging Face also. So this BERT for question answering is pre-trained and fine-tuned, both done for us. Now we need some tokenizer in the third line because we have text we want to tokenize and all those things. So all those things is done. So installing libraries is done. Okay, import library is done. Now we'll try to load the model. Very simple. When I say I try to load the model, it means I'm loading the weight, I'm loading the parameters of the models. So very simple. BERT for question answering from pre-trained. So this is the name of the model. BERT large and whatever. So BERT large, remember that 24 layer of transformer encoder. And uncase meaning there is no, it is case sensitive, insensitive, and yeah, masking everything, just forget about. And this is fine tuned on the, there is some data set called SQUAD, which is a question answering data set by Stanford University. So yeah, so already trained fine tuned model I have loaded. So no need to pre-train, no need to fine tune, everything is done with this line. Now when I have to load the tokenizer also. So the second line is loading the tokenizer. Done. Model is loaded. Even you can see we are saving something called, if we train again and again, it's a waste of energy. We are also trying to contribute to the pollution, right? Greenhouse and all those things. So yeah, a lot of people are working in that domain also, that how exactly we can reduce, because everyone is trained the BERT on their machine. So it will cause a lot of power consumption and all those things. So yeah, that's why pre-trained model, use it. It's a best way to go about. Now, as I already told, I will be testing this model on some data set. Means the question which I am considering is how to wash your hand. And there is a paragraph which I have taken from CNN article. So it was some Donald Trump said something and something. So entire paragraph is there. So this paragraph contains the answer for how to wash your hands. So yeah, now we'll tokenize this, apply the tokenizer. We'll apply the tokenizer. Just right now, I'm so entire. Someone has already implemented the library. When I am saying tokenization, there is a lot of step going behind. We don't worry about. We'll just use it for now. So so there is a tokenizer.encode. I'll tokenize question and text everything. Yeah. Also, this entire code which you see, apply some embedding. See, we have two things. We have question, we have paragraph. We need something to identify what is question, what is paragraph. So let's say for question, we'll say, see, in question, in this scenario, we have 5 or 6 token. For paragraph, we have something, let's say 500 tokens are there. So we'll use for each token, if it is a part of paragraph, we'll use 1. If it is a part of question, I'll use 0 as an indicator. Otherwise, how will the model will understand? So that's how the entire implementation was done. So that's why if you see in this entire segment, you can see I am doing creating a list of length equal to last line. You can say assert. When I am writing assert, so I am saying whatever the length of input was there, I am creating a list in Python of 0 and 1, as simple as that. So this entire thing, don't go into the detail. Just remember that there is a list which I am creating, which says if it is 0, it belongs to question. If it is 1, it belongs to paragraph. Very simple thing. Okay. Now data pre-processing done. Now what? I'll try to test. So very simple thing. We have the model given. In the model, we'll pass the input IDs, we'll pass the segment IDs, because we need to identify exactly it is a question or it's a paragraph. Then it will give some scores. The model will give some score, because as I told, model is nothing more than a maths. Here it will return the probability score, or some cases it returns some numbers also, depending upon how we implement and all those things. So those, everything is maths. So it returns some score. Then we try to find out which is the maximum score. So if you see torch.argmax, so it return a list of scores. As I told in transformer also, if we have I love Python, it may say I with a probability of 25%, M with some 75%. So it just, I'm trying to find out what's the best answer. So argmax means which probability score is the best, and then I'll try to convert those probability score into the word. And here you can see the model is giving the answer soap and water. And if you go to the paragraph also, you can easily read they are talking about the soap and water, that you should wash your hand with the soap and water. So I'll just reiterate the question. The question was how to wash your hands, and the article was something given in the CNN, and there somewhere in the article it mentioned wash your hand with soap and water. So yeah, see how easily we are able to use these pre-trained model, and even Google Colab help us to run the code without doing any setup, even if we don't have GPU and TPU, all those things. So yeah, this was the first example which I wanted to walk through. Okay. Yeah, so okay. Now, if you want to find out pre-trained models, so you can see, Aditya talked about few libraries yesterday. These are the libraries using which you can code from scratch. And Hugging Face also uses PyTorch. But these also provide some transformer model, pre-trained model, and everything. You can see there are a lot of pre-trained models over here. Like for our purpose, we have used something called Squad. Stanford question answering data set is there. So you can see, so this is a pre-trained model. And also you can see they have provided the API also to just, if you want to test how the model is behaving and all those things. Like in this scenario, my name is Clara and I live in Berkeley. This is the context of the paragraph. And the question is, what is my name? If I click on compute, it will run the model. Oh, it has already given Clara. So what's my name is, so the answer is Clara. So you can find out a lot of models. So if you want to try any other model, you can come here and let's see. Let's say what we can else try. Let's say some classification model if we have. Okay, not classification. Okay, let's say entailment. Not entailment भी नहीं है. Okay, let's say squad pay. Let's find out some other models. Let's say I'll search question. Okay. Yeah, so let's open this model. It also has some API. Let's try to compute what it does. So T5 is also one of the, so this model which I have opened here, this is also based upon the transformer model, and it came in this year only, and it's one of the great model. It also surpasses the BERT model. So yeah, it is trying to translate. So it is a translation model. If you want to translate from one language to another, that's what this model is doing. So yeah, you can go on this Hugging Face website and try to explore with the APIs. If you want to code, you can use Google Colab. Yeah, so these are the pretty good resources to just get started with the, at least at a high level, and then you can come to the coding part after you are done with these parts. Yeah, so these were the things I wanted to cover. Yeah, so Google Colab part is done. Hugging Face part is done. Okay, so till now I was trying to just motivate NLP, natural language processing models. I haven't talked much about how exactly we can use with some healthcare domain. But I have told one thing: if you have a healthcare domain, the model will learn. You just need the data. So let's take a simple example and see. So time series forecasting for COVID-19, you can use LSTM, you can use transformer, you can use some pre-trained model. So this I have taken from one of the paper. I haven't put the reference, but I should have. Yeah. So yeah. So very simple thing. I'll just try to explain the process and then you can use it with any model, whatever I have explained. We have raw COVID-19 data. Yeah. Then we can normalize the data. We can use LSTM. When I say stacked LSTM, meaning a deep LSTM, then we can also stack LSTM in both the direction. Those I haven't covered this bi-directional LSTM. You can consider we have a LSTM model from left to right and then another LSTM model from right to left, and we concatenate this. So this become bi-directional. Then also we have some convolutional LSTM. So you'll say convolutional. Usually we have a perception that convolutional is an image operation, but no. Convolutional is something which find a locality in the data, locality of reference. I mean to say locality means what things are related. So if we have a two-dimensional data, there we can use the convolutional LSTM. So these are the modeling which you can do. Then these are the hyperparameters. Like if you are using LSTM, kitne hidden layers honge? What is the sequence epoch size, meaning how many times I am going to iterate over the entire data set and all those things. And then we'll train the model, test the model, we'll repeat. Why there is this loop is that because we don't know the hyperparameters. Sometimes we can try with hidden layer, let's say 5 hidden layer. Next time I'll try to see with 7 hidden layer, because as we already discussed yesterday that these are the numbers which we don't know. These are the intuition, or let's say if we work in this domain more and more, we'll come to know about this hyperparameter, that this works better, this activation function works better. So all those things are like that. And then we'll try to evaluate the model on unseen data, how it works. So yeah, this is how you can apply to this time series data. And I think Government of India, there is some data you'll find out. I haven't put the link over here, but there is some data using those. You can find out how you can apply and all those things. So my idea was to summarize the model and let you know that healthcare is not something unique domain. Any domain, we can use the same model. Only thing that matter is data. If we have data, we can apply. Yes, so this is now. Yeah, I was going through some of the ACL is one of the conference which is a very good conference, A-star conference in NLP domain. And there I have seen a recent talk, 2-week-old talk, which talks about NLP for healthcare in absence of healthcare data set. So I haven't seen the full talk. I have gone through, and this talk seems very exciting since I found out the link today morning. So I thought let's put it in the slide. If anyone is interested in this part, link is already there. I'll share the slide. You can go and have a look at this. And it's a very good talk if you want to learn. And see, it's a very strange, which excites a strange part. Absence of healthcare data set, they are applying the NLP. So this is the exciting part. So you can go there and try to explore this part. Okay, yeah. So now, since this part is done, now the next part which exactly I want to cover is like the code of transformer. So you can ask if you have any question or any query till this point, so that I can clear. Yeah. Then I'll try to switch into the transformer model, since it's one of the state-of-the-art model in NLP. I'll just try to give a very high-level idea of the code. And yeah, you can write from scratch the entire transformer model. But before proceeding, if you have any query with respect to this, you can clarify. I'll try my best to answer. Okay, we can take at the end. I think let's go to the at least transformer code, and then yeah. Yeah. So this is the paper, Attention is All You Need, which talks about the transformer model, which I already discussed. You can see Google everywhere. Yeah. So this is a notebook which is annotated by Harvard students. So there is a paper theory also, and before theory they write the code. So instead of just showing the code, I thought let's show the paper, and alongside each concept they are writing the code. So it's better to look like that. So I thought let's at least give a very high level idea of what the code is. Because see, for me, when I was learning the model at a very high level, let's say transformer, until unless I coded the model, I seen the code, I was of the opinion it's a very complicated code, I can't be able to code. So at least even if I look at the code, it makes me feel better that at least I know the code, at least I can read the code. So yeah, that's why I have chosen to at least let's go over the code. Yeah. So as you can see, we have something called encoder decoder class, which we are defining first. And this entire code is in Python using the PyTorch library. Nothing else we are using. Okay, so here you can see we have an init constructor under which we are defining an encoder, we are defining a decoder. If you remember, in the transformer model, we have encoder decoder architecture. That's why we have renamed the class as encoder decoder. And as I told, we have encoder model, we have decoder model. And this encoder contains a stack of encoder and decoder. So, but this encoder over here, self.encoder, you can see this self.encoder is nothing but the set of encoders, self.decoder. Okay. I think, should I, because I can't write on the website, or this the website, but okay. Can I do anything else? Okay, I think I'll just iterate, just say the function name, you can see it over there. Okay, so in the init method, we have something called encoder layer, we have decoder layer. Also, I have talked about embedding, so those things are there. I'll talk about generator in a bit, yeah. Also, yeah, forward, encode, decode, let's just forget about it for now. Okay, so this generator, whatever was there, so you can see in the encoder decoder, init, in the init method, we have a last line called self.generator is equal to generator. So that generator is nothing but this. You can, if you can see this diagram. Okay, wait. I'll just. So it's just a name which I'm giving. So generator is this part. Just a name, you can give any name. This softmax and the linear. Yes. So you can see here, this is nothing more than we have a linear layer. Okay, sorry, let it come. So in the generator class, we have some linear layer. So this is the dense layer. Some people say it linear, some people say it dense. So this is a linear layer and we are applying the softmax. So this is what it is all about. So yeah, now, okay. So you can see in the encoder decoder, we have something called encoder, we have something called decoder. These are the two things we can see. Now I'll define the encoder class, because this encoder class is the exact thing which will contain those set of encoder decoder. If you recall, we have a encoder stack, we have a decoder stack, and that entire representation is this encoder class. Okay. So here you can see I am cloning. You can see in the class encoder, in the init method, you can see something called self.layers is equal to clones. So there is some encoder layer which I'll clone it n times. So this will become the encoder, the entire encoder side of it. And this forward pass is all about the passing the data. So as I told yesterday also, any neural network, there is a forward pass, there is a backward pass. So forward pass is about passing the input to those encoder layers. Okay. So I don't want to get into too much detail. I just tried to get an overview, the idea. At least we see the code at a very high level, we understand. So also the second layer was the layer norm. You can see the layer norm. Here the main idea of this particular layer was to normalize the data so that the training can become faster. So you can see the last line of the forward method in this layer norm class. So in the class layer norm, we have a def forward, and in the last line we have return self x minus mean. So I am subtracting the data with the mean, dividing with the standard deviation, and some more terms are there. So those detail I don't want to go into. I just want to say that this is a layer which I implement like this, and it normalizes the data in a very in a simple term. Okay, this sub-layer connection is about the residual connection. This part, this 1 second. This sub-layer, this arrow you can see here, this arrow, this is residual connection we say, because we don't want the input from input to fade if we are at the nth encoder and so on. So that is that part. So you can see each component can be coded like a class. So that's what it is. Okay, so we have defined a major two classes, encoder, okay, encoder decoder class, then encoder class. These are the major classes. Now we have to define the encoder layer class. You can see on the top of the screen we are defining encoder class. There we are using the self attention. You can see in the init method we are having self attention. As I talk, self attention is there, feed forward is there. So each encoder layer has two things, self attention and the feed forward. Okay, so these are the two things which I am defining. Then forward, as I already told, I do some operation and try to process the data. In decoder you can see in the decoder. So now I am talking about decoder part. Decoder also, here we are in the decoder class we have init method. There you can see I'm cloning the decoder layer n times, because a decoder consists of n decoder layers. Now decoder layer, you can see there we have self attention, then some other attention, which is here they have called source attention, but the other name for this is encoder decoder attention, and feed forward neural. So encoder layer and decoder layer, there is one difference of encoder decoder attention. And also at each layer we are defining forward. So those are some maths which I am skipping. Okay, even mask I'll skip. So these are the details of the attention, how defined. So at a very high level, attention finds out the similarity. You can see, I'll just talk about, you can see this formula, attention, Q, query, and V. So exactly you can consider relate it to the database. If we have a database of student, I want to query some record from that database, so we need some query. So here also we have some query, and there we have some primary key, that is like a key. So here also we have something like key, and whatever value it returns from the database, that is similarly we have something here called value. So we are taking the dot product between Q, means query, and key to find out how similar two words are, and then we apply the softmax to convert it into probability, and then apply it on somewhere. Okay, let's not go into the math detail, but basically attention, as I told, it looks at the left and right context, and how we define it mathematically. In a short, we define query, key, value, and we do some maths, and somehow we try to write these functions. So in a short, we can understand it like that. Okay, and as I told, we don't use a single attention, we have a multi-headed attention. So here we do a clone of a lot of attention layers and all those things. So yeah, that's out. And also I told there is a feed forward layer. It's nothing but a linear layer and its combination. Then we have a softmax layer, we have an embedding layer, we define the classes, and yeah, so this is how we do all those things. And positional encoding, I also talked about that we need some position to find out, like I say I am eating mango I is not a good. So all those things. So when I am showing the code, my only intention here is not to, because I took a week to code the transformer and understand exactly everything. In 2 hour session, what I wanted to do was like at least give you an idea that how this model can be implemented, so that if you have an interest, if you want to work in this domain, you can look at this paper, try to understand and see how it can be implemented. Different module. So this is the graph of showing the positional encodings, and this is the entire model. So I just walk through the entire model. You can see over here. Define make model, we have something called C is equal to deep copy attention FF. So come to this line where it is written model is equal to encoder decoder. As I told, transformer is an encoder decoder, inside which we have an encoder class and decoder class, right? And inside encoder class we have encoder layer, we have decoder layer. That's how we are doing. Now encoder decoder ke baad we have something called embeddings. You can see after that we are putting some embeddings layers, also some other embedding layer, and also the generator. You remember softmax output layer. So that's how this entire model is built. And there are some training, there are a lot of concepts by which I'm not going into the detail, but that's how the entire overall idea. I'll just show you one more diagram which is very much useful when we try to, so if you look at this diagram, you can see diagonally we are getting some patches. So that's what the attention is. When you can see on the y-axis we have words, on the x-axis also we have words. It is whenever we are getting a bright spot, it is showing. Whenever this example is for the machine translation, so they are showing when I am translating I am focusing more on these words. So so this is one of the thing you'll look in the transformer paper a lot, the attention paper a lot. So but it's hard. These are heat maps and all those things. So let's not go into the details, but these are entire paper. You can see how much thing they have put, and this is one of the best explanation you will find for this transformer. If you want, you can go through these things, and also, let's not go into too much detail of the transformer. Now, last thing which I wanted to talk was like, I talked about BERT model, which is based upon transformer. So there is some model called GPT-3. It came approximately 3-4 months before. And these are the links over here. You can see, you just generate the code. You just write something, it will generate the code. So this is also a pre-trained model. It can write the resume. You just write down the point, it will write a great resume. It can generate the meme. It can do a lot of things. If you write something in text, it can convert into latex, text to React code, text to SQL. So these are some of it can even write a comedy. So let's say if you so the GPT model is one of the largest NLP model existing right now. So they also have provided the API, but we have to apply for that if we want to use that. So here you can see this entire conversation is generated. So this is a conversation between Peter Thiel, Elon Musk, and the Larry Page. So if you look at the conversation, you'll just say this is a human conversation, but the entire conversation was generated by machine. And even the machine can understand a lot of things like emotion, like Larry leaves the room. So all those things are very much exciting, I feel, because GPT can do a lot of things, and let's see how we can use this model to make some good model which society can use or which can be helpful in any other way. So people are trying a lot of stuff with this poetry, music generation, and a lot of things using this model. So just wanted to introduce this model. It's way bigger. We can't train on our local system or something. It's a very good model. You just explore the links given over here. You'll find a lot of useful resources. Let me see if I can open anyone, because in ITV network, Twitter is blocked. Let's see if they allow this. Okay. Okay, I think it won't work now because some restrictions are there, what we can use and what don't. So yeah, this is from my side, and we can take any questions if we have. And I think I seen few questions coming down in the chat box. Like,
Yes, sir. Actually, there was a question from previous part of your lecture.
okay.
Yes, that was related to gradient, I guess. Yes.
Yes, ma'am, I'll answer that.
Yes, sir.
So
Sure.
gradient descent, exactly. So I'll just draw it over here to make a, see, ma'am told linear regression, right? So linear regression, we know, is something, let's say, very simple example. X attribute is given. We have to predict Y. So there are some data given. We have to fit some line like that. So here loss function, one of the famous loss function is a squared loss, meaning what is the model which it is predicting, what's the actual value, we'll square it out over, and the sum over all the example will take the average. So this is the loss function. Okay. Now the optimization algorithm, there is a simple solution. If you try to find a derivative, equate to 0, you will find a solution. So in case of linear regression, it's not always essential to use the gradient descent. I'll talk what a gradient descent is. It's not always essential. We can solve manually. We'll get some formula. We can code using those formula, done linear regression. But if you see this is so the modeling part is like something linear regression, like wx plus b, something like this we model. So that's a square term. So it's something like a quadratic function. So when we say the gradient descent, that's another algorithm. So there is an entire history, how it originates, slope and all those things. So instead of going into those details, let's just try to see what gradient descent exactly is. So at this point, let's say my parameters, so this is like, if you say this is on y-axis, we have loss, on the x-axis, we have some parameters like input x and some parameters here. So my loss at this point is this. So now you can see I have to minimize the loss, right? So I have to move along the direction of the slope. So that's a very simple concept of gradient descent. It says move in a direction opposite of the slope. If you do that in a step-by-step fashion, you will reach the minima. So there are other variation of the gradient descent, like batch gradient descent. There is something called stochastic gradient descent, which works example by example. So to summarize, it's not always important to, not necessary to use gradient descent for linear regression. It's optional because there is a closed form solution which we can find using the calculus. But even though if we want to use the gradient descent, we can use that. And the funda of gradient descent is that it move in the direction opposite. So this is the positive slope. We move in the direction opposite of the positive slope and we come at minima at each iteration. At each epoch, it will try to come here, maybe it can overshoot also, then come back. So there are a lot of things here. Learning rate, that's also one of the hyperparameter here when we are applying the gradient descent. So all those things let's not talk about, but this is the basic idea of gradient descent. Okay, yeah, so Aditya have written some, okay. So that's what the gradient descent is all about. And in the deep learning world, we use gradient descent and its variations. So in transformer, they are using some optimizer called Adam. So there is an optimizer called Adam and some optimizer called RMS prop. These are some optimizers which by default adjust a learning rate. So suppose I am at this point. If my learning rate is too high, I can come at this point. My learning rate is too high. It will oscillate like this. So this Adam and RMS form try to control those learning rate, and there are some other advantage also. It will try to keep momentum. So there is an entire research area. Yesterday we were discussing also what are the research we can do. So people have come up. So these are Adam and RMS prop. These were developed after 2014, I think 2014 or 2013. Why? Because there was a need. There were a lot of problems happening. in training and learning rate adjustment. So these method came into picture. So this is also optimization and all those things are a good research area to work on.
Thank you so much, sir. Participants, do we have any more questions? Okay, Suraj sir, I think there are no more questions. Your lecture is inclusive of all the points we require for machine learning for healthcare. So, can I proceed with the conclusion part?
Yes, ma'am. I think I'm done with my part.
Okay, okay. Sir. So, sir, it was a very informative hands-on session. It will definitely help us for enhancing our skills. Thank you very much for your valuable insights on machine learning for healthcare. As we come to the closure of day 5 sessions, I would like to thank Principal Sir, Vice Principal Ma'am, HOD Sir, and the entire organizing team for such a wonderful event. Thank you, Suraj Sir and Aditya Sir, for sharing your knowledge with us. We are very much grateful to you. Thank you so much. See you all participants tomorrow. Thank you so much.
Thank you, ma'am.
Thank you, sir.